Welcome back, everyone. Houston Math Prep here to talk to you about initial value problems for antiderivatives and finding particular solutions. So let's say we have the velocity of some object we know, so we know v of t is equal to negative 32t, and we want to find the position function s of t. So this is about using an antiderivative. Remember that if we take the derivative of the position function, we get the velocity function. So that really tells us then that the antiderivative of the velocity function, with respect to time in this case because t is our variable, right? That's actually going to give us our position function. So if we take the antiderivative for this one here, so we take the antiderivative of negative 32t dt, that should, of course, give us the position function. Now we can, of course, bump out the negative 32 constant multiple, so we could say negative 32 out front if we want, t dt. We certainly don't have to, but we could do that. We keep the constant multiple of negative 32, though, and the antiderivative of t, if we think of this like t to the 1, then that's a power rule, and that says we'll get t squared. We'll divide by that new power of 2, plus our constant of integration. And then that means we'll get that our position function, the antiderivative, if we reduce this, is actually negative 16 t squared plus c. And remember that c is some arbitrary constant. It could be positive, negative, could be 0, it could be a whole number, a decimal, could be many different things. So there are many functions that have a derivative of negative 32t, and these are all of them. So we call this family of functions that satisfies having a derivative of this. We call this the general solution. In other words, we're not sure, just given the information that we have, what our constant really is. If we now change the situation and give you more information, so we give you the velocity is negative 32t, but then we give you some additional information about position, then we're actually able to find the particular constant that goes with this situation. So think about, I have my same v of t, right? So my v of t is negative 32t, and we already took the antiderivative of this just now, right? So we took the integral of v of t, and that gave us the position function, right? So we just found that our position function was negative 16t squared plus c. Now what we have here, this is called an initial condition. So we know a condition, an extra piece of information about what's going on with our s function, our position function, okay? This initial condition here says when I plug in 1, I get an s value of 80, or in other words, when t equals 1, then I know s equals 80. And what I can do is use this initial condition, I can plug it into my position function, my s of t, and then I can actually solve for the constant, and that will give us the particular solution. So let's go ahead and plug these things in and see what we get. So if I plug in 80 for s, so that says 80 equals, if I plug in 1 for t, that would be negative 16 times 1 squared plus c. That would give me 80 is equal to negative 16 plus c. If I add 16 to both sides, then I get that c is actually 96. If I didn't have this information, I wouldn't know what c is, but now I know what c is, so let's go ahead and take that information and put it in there. And so we'll say our s of t, that includes this initial condition information, is actually negative 16t squared plus 96. So we know the particular constant that satisfies also this condition. And this is called our particular solution. Let's look at one more example. We're actually giving you two conditions here. So we have the acceleration function for an object, a of t is negative 9.8. We want to find the position function, s of t, and we're given two conditions. We're given v of 1 is 6 and s of 0 is 24. So we're starting with a of t. Think about we have a of t. How do we get to the position function, right? The position function, it turns out, is not just one step away from a of t, right? If I take the antiderivative of acceleration, then that actually is going to give me the velocity function. And then I would have to do what I did before, right? So then the antiderivative of the velocity function, if we integrate that, then we'll get our position function. These conditions here, these initial conditions, are actually going to help us solve our constants along the way. So let's go ahead and do this first part. Let's go ahead and find the antiderivative of a of t. That'll at least give us the velocity, and then we can do the second part after that. So the first part, if we take the antiderivative of just negative 9.8, and because it says it's a function of time, we should integrate this dt, not dx. So if we take the antiderivative of this, in other words, with respect to t, what gives us a derivative of just this number, negative 9.8? And the answer is negative 9.8t would give us a derivative of negative 9.8, plus our constant, could be some constant there. And now remember what this is. This is actually our v of t, right? So this is our general solution for velocity. And now if you look back at the conditions, which of these do we use to solve c? Well, we use the one that's about velocity. This one says v of 1. This one says s of 0. This is about position. I have velocity function, so I need to use v of 1 is equal to 6 at this point. Okay, so remember this says when t equals 1, then v equals 6. So you'll plug that information into your velocity function, and we'll solve our constant. So we'll plug in 6 for v, equal to negative 9.8. T is 1, so we plug in 1 here, plus our c. We'll go ahead and this is negative 9.8. We'll add that to both sides. So this will be 15.8 is equal to our c. So we'll take this information for c, we'll put it back in our general solution. That will give us the particular solution, at least for velocity, right? So our v of t is then negative 9.8t plus 15.8. So that part is done. Now we need to do our second part, which is now take the antiderivative again and get to position. So if I take the antiderivative of this velocity function, so that will be the antiderivative of negative 9.8t plus 15.8, integrating again with respect to t. If we do that, then think about what happens here. This is like t to the 1, so we'll keep our constant multiple of negative 9.8. We will get the power going up by 1, so we'll get t squared, divide by the new power, plus what will give us a derivative of 15.8? Well, it'd be 15.8t, plus our constant. I'm going to go ahead and clean this up. So remember, this is our position function now that we've integrated, right? So our position function, s of t, is actually, if I divide this by 2, we'll get negative 4.9 t squared plus 15.8 t plus our constant. And we can solve this constant. This is our general solution for position, but we can solve because we have a condition that tells us about position. So this s of 0 equals 24 tells us when we plug in a value of 0 for t, we will get that s is equal to 24. So if we plug that information to the s of t here, we can solve this other constant as well. Let's go ahead and do that. I'll do that over here. So we'll say 24 in for s equals negative 4.90 squared, right? So that'll be 0. Plus 15.8t, which is 15.8 times 0, plus our c. So we plug in 0 for t. This becomes nothing. This becomes nothing. It looks like we just get 24 is equal to c here. And now I can take that value for c and put it back in my general solution where I had my constant, and that'll give me the particular solution for this, right? So we'll get our position function s of t is negative 4.9 t squared plus 15.8t plus 24, and that's our particular solution for position. And this function for position here satisfies both of these conditions, that at time equal 1 second, the velocity is 6 of whatever units we're dealing with, and at time equal to 0, then our position is equal to 24, whatever units we're dealing with as well. All right, everyone, hopefully this helps you with your initial value problems and finding particular solutions. Thanks for watching. We'll see you in the next video.